So thank you for choosing to attend my talk, and thank you to the organizers for inviting me to give this talk. And I'll be talking about backtesting and error metrics for modern time series forecasting. And before I dive in, I'll give you a brief introduction to myself. So my name is Kishan. I've recently started working as a machine learning and data science consultant. I spent the last 10 years working in retail, e-commerce, and finance, working on a range of problems from machine translation, pricing optimization, and last but not least, time series forecasting. Before that, I did a PhD in physics. I've also created a couple of online courses on time series forecasting in collaboration with Soledad Ghali. You can find that in the link there. And my slides are on GitHub, and they're also on the PyData schedule as well. So what is this talk about? So I'm going to be talking about backtesting. This is where we want to measure the performance of a forecasting model on historic data. I'll be talking about error metrics, which is how we quantify our forecasting accuracy. And I'll be talking about this in the context of what I call modern time series forecasting. And so this is where we typically are working with a large number of related time series which have a heterogeneous set of characteristics. And so by the end of this talk, I hope you'll be able to make better decisions when deciding which backtesting strategies and error metrics to use when working with a complex forecasting problem. So I want to start by talking a bit about modern time series forecasting, by which I mean a use case where you have a large number of related time series. And so this contrived example here is a retail example. So imagine you're a fashion retailer, you have a large catalog of products, potentially tens of thousands on your website, and you're interested in predicting the future demand of those products. Now, these time series can contain a large variety of different characteristics like trend, seasonality, outliers, intermittency. This is where the time series looks more count-like and you have a lot of zeros, like with the jackets at the bottom. You can have a lot of missing data, and this is actually the norm in a lot of retail problems where products have a finite life cycle. They'll be online for a period and they go offline, they might run out of stock. So you have a lot of time series that come into and out of existence rather than necessarily a single long time series. There's also a lot of interrelationships between these time series. So just because they're on the same website or store, for example, they could be affected by promotional activity. You think that being in certain categories would also relate the time series. So t-shirts will be more similar to each other than hats. And so typically you would train a single, what's called a global forecasting model on the whole set of time series so it can learn these interrelationships. You might also be interested in the hierarchical aspect of the problem. So a lot of the times you won't just potentially predict things at a product level, you'll aggregate and look at a category level, at a total level, or by geography, and you want things to be consistent in that sense as well. So all these things make it a lot harder to do backtesting and to select appropriate error metrics. And so it's a lot more difficult than just having a single airline's type of time series that you're trying to forecast into the future. So typically what you do is you actually concatenate all of these time series into a single table. You'd extract a set of features and a target variable and plug those into a traditional machine learning model like a gradient boosted tree. Deep learning models are becoming a bit more popular in this area. In my experience, they haven't really proven to be a lot better than just using a gradient boosted tree, but there's a lot of work going on in that space. If you want to learn more about that topic, about how you extract features and convert a forecasting problem into a more machine learning regression problem, I gave a talk at PyData a couple of years ago, and you can find that on YouTube already. In this talk, I'm focusing on backtesting and error metrics and less on the modeling. So let's dive into backtesting. So what is backtesting? Backtesting is where we want to measure the performance of a forecasting model on historic data. The objective is that we want to estimate the performance of our model on future data. So typically what we do, we have our time series, we split at some point in time, we train our model on the data before that point in time, we'll make some forecast into the future, and we'll compare the forecast and the actuals. Traditionally, when we work with tabular data, it's quite common to randomly shuffle the data into training and test sets. You can't do that when you have the time dimension, and this is because the rows are no longer independent. You don't want to put data from the future into your training set and data from the past in your test set, and then have a model use the future to predict the past. That's a form of data leakage, and you won't have a very good estimate of your true model performance. And so backtesting is also known as time series cross-validation, and I'll show you why. So what you typically do is you order your data set over time, and then you'll have multiple splits where you split at certain points in time, and you move that window forward. And so you train your model on the training fold within a split, and then you predict on the test set, and you have an error metric for each split, and then you average the error metric. So this all looks great. But when you actually do this with large data sets, with multiple time series, with lots of missing data, you'll find this is very time consuming, memory consuming, and very error prone. And so what I want to talk about is how we can deal with some of these issues. Now you could try parallelizing this. I'm going to talk about some alternative backtesting parameters that you can change to help overcome some of the time and memory consumption issues, and also recommend some libraries that help with the potential edge cases and errors that you might come across if you were to implement backtesting yourself for these kinds of time series. So the parameters I'm going to talk about is the training window type, the step size, and the refitting frequency. I'll go into more detail in a second. And what we'll find is that choosing our backtesting parameters is ultimately a trade-off between trying to get a reliable estimate of our model performance versus the time and memory consumption of backtesting. And I'll illustrate this in just a moment. So one of the parameters I discussed earlier is the window type. And so in most textbook examples of backtesting, you'll just see an expanding window as you go through each split. An alternative is to use a rolling window where you keep that window size fixed. So what are the pros and cons of these approaches? Well, with the expanding window, you're using all of your training data, which is nice. It will reflect what will happen in practice if you are going to retrain on your entire data set as you go forward in time in production. The cons is if you're using your entire data set and you have quite a lot of data, you're using a lot more memory, it takes longer to train the model. And if you have very old data, that may not actually be very useful. It may not actually be giving you a lot of value for forecasting purposes. And so a typical strategy is to only use a rolling window, and so you end up using less memory, it's faster to train, and you will also focus more on recent data, which can potentially also give you a better model. The downside is you're not using all the data you potentially have for training. The other parameter I mentioned was the step size. So once again, in most textbook examples, you'll just see these splits, you'll move forward one step at a time. That step size is actually negotiable. You could do multiple steps, and this would reduce the number of splits you have, and you can traverse your time series more quickly. So the advantages of having a very small step size is you'll have a larger number of splits, which will give you a better error estimate. The downside is you have more splits, and therefore it takes more time and memory. If you have larger step sizes and you've got fewer splits, and therefore it takes less time and memory to run backtesting, but you will get a worse error estimate. Now, when you're working with a very small step size, it's very likely that the errors are going to be quite highly correlated as you move one step at a time. So you can actually increase the step size without reducing the how good your estimate of the error is. And so it's not actually that much of a trade-off. And so I'd never, almost all the time, I'd never recommend moving forward one step at a time. I think it's not really necessary, but it depends on your time series. But it's an easy way to save time and memory. The other one which doesn't get discussed as much is actually the refitting frequency. So typically you will fit a model on each split and make a prediction for every split. You could actually choose to do an alternative approach where you would train a model on your first split, and then on the second split you choose not to refit the model, but use the model that you trained in the previous split and still make a prediction. So you're reducing how often you're fitting the model, and that can save you training time. And so if you want to refit at every step, that will give you a better estimate of model performance if you tend to refresh your models in production very frequently. But it takes a lot more time because at each backtesting split, you're going to have to retrain your model. Refitting periodically obviously takes less time, but you will have a worse estimate of model performance if in production you are in fact refreshing quite frequently. So choosing backtesting parameters is therefore a trade-off between how reliable you want your error estimate to be against time and memory. And how much of that trade-off you typically make depends on what you're doing. Are you trying to pick the best forecasting model? Are you doing hyperparameter tuning? Are you trying to measure the forecasting error very accurately for a critical use case? And so depending on these, you'll choose to do something different. If you want a very accurate error measurement, you'll pick the parameters accordingly and you'll take the hit on time and memory. If you're doing model selection, if you have a lot of time series, if you're doing hyperparameter tuning and for each hyperparameter you want to run backtesting, you probably want to adjust the parameters so that backtesting takes less time. The other comment I want to make is you want to have your backtesting process to try and reflect what actually happens in production. And I'll give you an example from fashion. So you typically want to predict what set of clothes are going to be selling a season from now, which can be 6-7 months into the future. But buyers need to decide what they're going to buy now, 6-7 months in advance. So there's a huge gap to when you train your model and produce your forecast versus the forecast horizon when it's actually going to be used. And so there's a gap. If that's the case, then you want your backtesting procedure to also reflect this because that will give you a better error estimate for your actual use case. Now I want to come on to some of the edge cases when you're working with time series data that looks a bit more messy and in my experience a bit more real world. So you typically have a split somewhere when you're doing backtesting and then you'll run into all sorts of issues. So typically what you do is you're going to create your features from some past window of data, like using lag features or some window features in the past, like a rolling mean, for example. But then you'll see that there are issues. So if we look at the green time series, that product doesn't exist at train time, but it will exist in your forecasting horizon. The red hat, it does exist at train time, but it no longer exists in the forecast horizon. And so when you are implementing backtesting yourself, you have to handle all of these various edge cases because the number of time series at a given point in time isn't actually fixed in a sense. You also have issues where if you go further, if you had a different split here, for example, you might still have some data, but not enough to create your features. And so you may have that product, it may exist, but you don't have enough data to make a prediction for that product yet. And so I recommend using some open source libraries. A nice one is skforecast, where you can define a forecaster object and you can supply any scikit-learn compatible model like a random forest, decide which features you want to use, like some lag features, and then pass that into a backtesting function and you can pass the various parameters that you want and then it will do the backtesting for you and give you your metrics and predictions, and that's quite nice. It's all written in pandas. Funktime, on the other hand, is written in polars, so it's quite fast. It has a very similar API. You just define a forecaster object. It can be a linear model, it can be a gradient boosted tree or whatever. You define some features and you pass that into a backtesting function, and then you have your error metrics. And so there's quite a few libraries out there in Python now that help to do forecasting with machine learning. So now I'm going to talk about error metrics. And anyone who's worked in forecasting knows there are a lot of forecasting error metrics. In this great review paper alone, and this is for point forecasts, not probabilistic forecasts, there were over 40 different metrics documented. And so the question arises, why are there so many error metrics and how do I actually pick the right error metric for my own use case? So to answer the first question, it helps to look at the structure of most error metrics. They share a common pattern, and what we'll find is that the properties of an error metric depend on essentially three main components that make up most of these metrics. And so I'm going to dive into those three components by looking at an example, the mean absolute error. So a very common error metric, and you can break it into three different components. One is called the base error. So in this case, for the mean absolute error, we have what we would call the scale-dependent base error. This is just the difference between the actual value and the forecasted value. It's scale dependent because if the value of the time series is typically larger, then the error is larger. You then apply a positive transform like the absolute value or the square because you don't want your negative and positive errors to cancel out when you apply the mean. So you make the error positive, and depending on what you use, you get your metric has different properties. The absolute value is less sensitive to outliers than the squared error. Squared errors typically optimize on the mean. Absolute errors typically optimize on the median, for example. So as you choose these different components, your error metrics will have different properties. And then you apply some aggregation operation like the mean. You could also choose the median, the geometric mean, a weighted mean. So you can see that all these different permutations results in a very large number of different error metrics, and depending on the different components you use, the properties of that error metric at the end can be quite different and make it more suitable for a given use case. I just want to go through one other example, the mean absolute percentage error. And so this is where you have a different base error. So you take your difference between your actual value and your forecasted value, and you divide it by the actual value to make it scale independent. Now, who thinks this is a good error metric? Good, because it's a terrible error metric for multiple reasons. One is if the actual value is 0, this metric explodes and is not defined. It's also not symmetric to under and over forecasting, and so if you optimize on this metric, your forecasts are biased. And so there are many reasons why you shouldn't use this metric, and I'll go into some alternatives later. But I just want to drive home the point that depending on which components you use, your final metric has different properties, which makes it more or less appropriate for a given use case. And not all metrics strictly follow this kind of pattern, but most do, and it helps you build an intuition. So how do we go about picking our error metrics for forecasting? Well, we have to think about our use case and the properties of our time series and match them with the properties of error metrics. And so if we're doing modeling versus reporting our forecasting accuracy, we'll choose different error metrics. If we're reporting, we might want something more interpretable, for example. Now, our use case, we might actually care about scale in some cases. So we care more about larger time series than smaller time series. In other use cases, the scale is arbitrary. If you're forecasting temperature, the scale is arbitrary. If you're forecasting the demand of products, you care more about the products that are selling in large volumes. You might care about the hierarchy. You might care about over and under forecasting differently. Maybe over forecasting has a larger penalty than under forecasting. And you also have to consider the properties of your time series. So do you have level shifts, intermittency, outliers, seasonality, trend, and so on. And so I'm just going to go into some of the main properties of error metrics that we need to consider to be able to match our use case to particular error metrics. So one is scale dependence. So some error metrics will increase with the scale of the time series, like the mean absolute error or the root mean squared error, and others are scale independent. Sensitivity to outliers, so absolute errors like the mean absolute error is less sensitive to outliers than the root mean squared error, for example. Symmetry to over and under forecasting, and there are actually two different ways that this can happen. So one is where the forecast is an equal amount above and below the actual value, and you want your error metric to give you the same magnitude error, irrespective of whether you're below or above. The other one is if you keep the magnitude of the error between the forecast and actual values fixed, and you swap the actual and forecasted values. So there are two different senses in which a metric can be symmetric to over and under forecasting, and we'll find that some are symmetric to both, some to one, and some to neither. Can it handle zeros is a big one, especially when you're working with a large number of time series. You're bound to sometimes get some time series which take on the value of 0, especially the case when you're working with intermittent time series. And I showed you earlier that the percentage error can't handle zeros, and there are alternatives, and I don't recommend the SMAPE either, which is called the symmetric mean absolute percentage error, which is a very common one, and it's not actually symmetric either. The name is incredibly misleading. Also, some error metrics optimize on different parts of the distribution of the target variable. The RMSE optimizes on the mean absolute error on the median, and I'll show you the repercussions of that later. So this review paper I referred to earlier has a fantastic flowchart which looks at your use case and your properties, and you go down the flow diagram and it will take you to which error metrics it recommends for a given use case. Now, I don't have time to go through every branch of this flowchart, so I'm going to deep dive into some of the most interesting and important parts in my opinion. So one use case I want to talk about is multiple time series where the scale matters. So let's go back to a kind of a retail context. So we've got a bunch of products and we want to predict their sales into the future. What properties do we want from our error metric? We want larger time series to contribute more to our error than smaller time series. So there is a degree that we want scale dependence. Typically we want symmetry to over and under forecasting. We want to be tolerant to zeros because there's some products that just don't sell very well. And we also want to be able to compare our errors for different subsets of time series which may take on different scales. We might want to ask the question, do we forecast t-shirts better than hats? And the average value for t-shirts might be different from hats. And so there's a sense that we actually want some scale independence. And how do we square that circle? And I'll show you later. And so typically the RMSE and the mean absolute error actually cover almost all of these requirements other than this last part about comparing different groups of time series on different scales. And so how do we overcome this? I'll talk about it now. So let's imagine you've got a couple of time series and you have your forecast horizon and you've forecasted 3 points into the future. We've got 2 time series. So we've got these individual forecast errors. What can we do? So one thing we can do is called averaging. We will compute our scale-dependent error metric, like the RMSE, on each individual time series and then simply average them. Another approach is called pooling, and this is where we will combine all of the errors across all the time series and then compute our scale-dependent error metric, like the RMSE, over all of the errors. And so to make that more concrete, it would look something like this. So in the pooling case, you see that we're just bringing in all of these individual errors to compute the RMSE. So the pooling actually is quite cool. So what you can do is you can pool your scale-dependent errors over multiple time series and then scale that by the mean of all the time series. And that gives quite a neat metric that's been used in a few papers. So this is called the normalized root mean squared error. So it looks intimidating, but it's not. All you've done is you've pooled all your errors to compute the root mean squared error across multiple time series, and then you divide by the average value of your time series in your forecasting horizon. The equivalent for the mean absolute error has a different name. I'm not sure why. It's called the normalized deviation, but it's essentially the same thing. The mean absolute error in the forecast horizon pooled over your entire data set divided by the average of the time series. And that gives us all the properties we want. Larger time series will contribute more to the error than smaller ones because of the pooling. It's symmetric to under and over forecasting, and it can tolerate zeros. The only time it will fall over is if all of your time series are 0 in the forecast horizon. There's that one edge case there. And these metrics can also be used to compare errors between different subsets of time series, because you can just recompute this average of the time series over your different subsets to rescale. And so that's quite neat. So what if we're dealing with multiple time series where the scale is arbitrary? We might have a bunch of sensors reading temperature, and the scale is not that important. So what we want from our error metric is we want each time series to contribute equally regardless of scale. We want symmetry to over and under forecasting typically. We still might want to be tolerant to zeros, and we want to be able to compare errors for different subsets of time series again. So we need to use what are called scale-independent error metrics. And so I need to introduce a couple of those. So earlier I talked about the percentage error, and this is where we divide the difference between the forecasted value and actual value by the actual value. And the percentage error, as I explained earlier, is not a great metric. But there is one version of it that is actually quite useful. It's called the weighted mean absolute percentage error. And I highlight the colors because it refers to the different components. So our base error is the percentage error, the positive transform is the absolute value, but now we're going to take the weighted mean. What do we select as the weights? If we use the weights as the value of the actual value of the time series itself, then through some algebraic trickery, it just becomes the mean absolute error divided by the average of the time series again. So it becomes the normalized deviation metric that I introduced earlier, but just for a single time series, and it's got a clear interpretation also as a scale-independent percentage error metric. And this has a bunch of nice properties. So it's scale-independent when comparing different time series. It's interpretable. It's still a percentage error metric. Symmetric to over and under forecasting, unlike the mean absolute percentage error I introduced earlier. It's well defined when the forecasted value is 0 or when some of your actual values are 0. The only time it's not well defined is when all of your actuals are 0 in the forecast horizon. So this is quite a nice scale-independent error metric, which is resilient to a lot of kind of exotic properties of time series. The other one that's quite popular are what are called scaled errors. And so this is where we're going to rescale by a naive forecast on the training set. So we compute a naive forecast, which is where you use the previous observation as your forecast. You compute that on your training set. You'll then compute your error metric on the training set, and then you're rescaling by that. Do people follow what I'm saying, or have I lost everyone? Okay, cool. Thanks. And so that gives you a new base error, our scaled error. And so this creates a couple of error metrics, the mean absolute scaled error and the root mean squared scaled error. And so this also has nice properties. It's scale independent, symmetric to over and under forecasting, well defined when your actuals or forecasts are 0. The only time it's not well defined is when your time series is 0 for your entire training set. Actually, another caveat, or when your time series is constant in your training set, because the naive forecast that you typically use is the previous observation, and so if you were to compute the naive error and it's constant, the error is 0, and so you're dividing by 0 again. So that's the only time that this error metric kind of falls over. So these are two cool scale-independent error metrics. And so when you're working with multiple time series, what you'd do is you'd compute them individually for each of your time series, and then you can take the average of those. Now I want to talk about a slightly different topic, hierarchical forecasts. So typically we'll have actual values at some level of a hierarchy, y1 and y2, and then we have another level of the hierarchy, which I denote z. And so z is just the sum of the time series below it. And typically what we want are called coherent forecasts. And so this is where we want to produce a forecast at the bottom level and at the top level, and we want them to sum together. And so a typical way of doing hierarchical forecasting, one approach is called bottom-up. So you make a forecast at the bottom level of the hierarchy, and then you sum them together to get the forecast at the higher level, and you have that property of being coherent. So we want the most accurate forecast at all levels of the hierarchy. And so we would just pick an error metric, and then we would create a forecast, and we're going to minimize the error of that metric on both of our forecasts at the bottom level. And then the question I want to ask is, does that also minimize the error at a higher level of the hierarchy? If we created the best possible forecast for that error metric at the bottom level, does that create the best possible forecast for that error metric at a higher level? And I guess because I'm asking the question, the answer is no. So it turns out that there's a great paper on this, I've listed it below, that the only error metric which satisfies that property are functions of the squared error. So this is like the root mean squared error, the root mean squared scaled error. They're the only metrics that would satisfy this property. If you were to optimize on, let's say, the mean absolute error or the mean absolute percentage error, and you created the best possible forecast on those error metrics, at the bottom of the hierarchy, it will not optimize your forecast further up the hierarchy. And that's very frustrating because your stakeholders will ask you, well, if we got better forecasts at the most granular level, why isn't my forecast at a higher level getting better? And so pick a forecast metric like the squared error, less interpretable to stakeholders, but when you're doing the modeling, it's a better metric to use when you're working with hierarchical forecasts. And lastly, I just want to talk about intermittent time series. And so this is where you have lots of zeros and then occasionally have non-zero values. And I mentioned earlier that the mean absolute error minimizes on the median. So some error metrics actually minimize on the median. And so in the case of intermittent time series, it means you would produce a forecast where you just produce zeros because the median for this kind of data set is 0. And so if you're doing demand planning and you've got products that sell at low volumes, you're just going to tell your demand planner, this product is never going to sell. And that's not particularly helpful. If instead you're going to use the root mean squared error, which optimizes on the mean, you will actually have a best forecast, which is a non-zero value. It might actually be fractional, a decimal, like 0.5, and you can interpret that as the average number of units you'll sell on a given week. And a demand planner can then roll that up to multiple weeks and actually make useful decisions. And so this is another part where we care about the property of the error metric and how it's relevant to the use case. So just to conclude, modern time series forecasting, as I define it, is when we are forecasting lots of related time series and we're using a global forecasting model to do so. Selecting the backtesting parameters is a trade-off between reliability and speed. Selecting our error metrics requires pairing the properties of our data and use case with those of error metrics, and error metrics aren't as terrifying when you realize there is a common structure that error metrics are built of, and if you understand the components that make up an error metric, you can pretty much design, it's like cooking, you can choose the ingredients to get the kind of error metric that gives you the result that you want for your use case. And there are many Python libraries available to help support with using machine learning for forecasting. If you'd like to learn more, we have a course on training data in collaboration with Salad Adgali. I've got some references and open for any questions.